So in the last lecture, we talked about kinematic motion in 1D, or how things move in one dimension, right? We talked about positions in one dimensions. We talked about average velocities and average speeds. We talked about accelerations and all that good stuff. And we solved a couple of problems with that. But today we'd like to focus on kinematics in 2D. So now we're going to be looking not only at an x-axis or y-axis, but we're going to look at both of them simultaneously. So to begin with, I'm going to revisit the idea of position in a 2D coordinate system. So position of an object in 2 dimensions. The position is the location of an object with respect of an object with respect to a reference frame which we call a coordinate system. And we're going to denote the position of an object in 2 dimensions by a position vector r. So we denote the position vector, the position of an object in a 2D coordinate system by a position vector which we denote by r. So now I'm going to draw a picture to sort of show what I'm talking about. So here I've drawn an x and y axis, right? This is an example of a 2D coordinate system. And we're going to denote the position of a vector, or the position of an object, by a position vector r. Right? And if we're writing this r vector out as coordinates, it's going to have some x position, and it's going to have some y position. And so we represent it as this pair of coordinates, just as we saw in the first lecture. But we can also represent it as some amount x in the x direction plus some amount y in the y direction. All right, so hopefully, like, this is all stuff that's been retained since the first lecture. But this distance here is the x component of r, and this amount here, right, on the y-axis, this little bit, is the y component of r. So when referring to these position vectors, I'm typically going to use notation that looks like this. So just like we did last lecture, we defined the displacement of an object in 1 dimension as its final position minus its initial position. And we can do something similar in 2 dimensions. So next I'm going to talk about displacement in 2D. Let me go down a little bit. So the displacement of an object is still the same, right? Similar definition. So you have the displacement of an object in 2 dimensions, which we write as delta r, is equal to the final position of the object minus the initial position. So the definition is still the same, but instead of working with 1-dimensional vectors, we're working with R, which is a two-dimensional vector. Or we are saying that R is a two-dimensional vector. So we can actually expand this out a little bit. So this first vector R, our final position, this one right here, has components x in the x direction plus y in the y direction, right? Whatever those are. We have minus our initial position vector, r naught. So that is going to have some amount x naught in the x direction. I might need to move some of the stuff over. Just do that. All right, so our position vector r naught, our initial position vector, has a component x naught in the x direction plus y naught in the y direction. Right. And so if you guys remember what we did in the first lecture, in order to subtract two vectors from one another, we just take this minus sign and we treat it as a plus times -1. This is going to be equal to the vector r, the final position. So that's going to be some x amount in the x direction plus some y amount in the y direction plus -1 times the vector r naught, just components x naught in the x direction and y naught in the y direction. Right. And so we know how to multiply a vector by a number. We just take that number and we distribute it through to each of the components of the vector. So in this case, this becomes our final vector r. It remains unchanged. It's going to be x in the x direction plus some amount y in the y direction plus this new vector, which is minus r naught. So this is going to be minus x naught in the x direction plus minus y naught in the y direction. And so now we're just adding two vectors together. And the way that you do that is you add their x components together, and that's all in the x direction. And then you add all their y components together, and that's all in the y direction. So our displacement becomes x plus negative x naught, or minus x naught in the x direction, plus y plus negative y naught, or minus y naught in the y direction. And there you have it. This is our expression for the displacement in 2 dimensions. So notice that we can actually simplify this because this is similar to what we've seen before. So we can go one step further and note that x, the final position, minus our initial position, is just the displacement in 1 dimension in the x direction. And similarly, y minus y naught is just the displacement of our object in 1D, but it's in the y direction. And so this kind of gives us a taste of how we're going to go about approaching motion in 2 dimensions. We really focus on 2 one-dimensional cases. So we focus on things happening in 1 dimension in the x direction, and then we focus on things happening in the y direction, and we sort of merge them together at the end. So in our case, our displacement vector r is given by the displacement in the x direction plus our displacement in the y direction. And so if we're going to take as our definition of displacement in 2 directions or 2 dimensions, I'm actually going to use this last line here. So this last line is our displacement in 2 dimensions. So just like we did with position and displacement, we can continue this process on by looking at the average velocity in 2 dimensions. So let's look at that next. You're going to notice that a lot of the stuff that we're talking about today is not going to be incredibly different from the stuff that we learned in the previous 2 lectures. It just has this extra twist of now talking about 2-dimensional things instead of just 1-dimensional things. And here is really where we get to see the power of vectors come into play, because we couldn't really see the use for vectors in the previous 2 lectures, but here we're going to start see them being more and more useful to us. So please pay attention to that as we go throughout the lecture. So the average velocity can be defined in 2 dimensions as well. So we say that the average velocity is equal to the displacement of our object, right, divided by the elapsed time. Now note that the displacement of our object, delta r, is defined as our final position, r, minus our initial position, r naught. And this is all divided by the elapsed time, which we call t. We can actually break this down even further, right? So notice how we have defined the displacement in 2 dimensions, right? And what we've just done, we know that r minus r naught is equal to the displacement of x in the x direction plus the displacement of y in the y direction. So let's actually write that down. So we have r minus r naught is equal to the displacement of x in the x direction plus the displacement of y in the y direction, all divided by elapsed time. So we can rewrite this again as delta x divided by t in the x direction plus, here, let me just parenthesis that off, plus the displacement of y divided by t in the y direction. But notice that the displacement of x divided by the elapsed time is the average velocity of our object in the x direction. So I'm going to call this, the thing in the first set of parentheses, Vx, right, our velocity in the x direction. And I'm going to call this thing in the second set of parentheses our average velocity in the y direction. So V sub y. Right. And so I'm just going to rewrite the things that I've just defined here. So now I'm going to rewrite the things that I've just defined here. So we have our average velocity in the x direction. It's just our displacement in the x direction divided by the elapsed time. And our average velocity in the y direction is equal to our displacement in the y direction divided by time. And so we can go one step further than the average velocity by talking about the average acceleration. So the average acceleration, right, this is in essence kind of a recap. Acceleration is a little bit of a recap of what we did in the last lecture, but now we're just looking at stuff in 2 dimensions. So again, all of this stuff should be familiar. So the average acceleration, we denote by a, right? And that's equal to the change in our velocity, where again, now our velocity is defined in 2D. It has both an x and a y component. So it's our change in our velocity divided by the elapsed time. But notice that since our velocity is defined in 2 dimensions, we can rewrite this as the change in velocity in the x direction divided by the elapsed time. Right, so all this is happening in the x direction, plus our change in velocity in the y direction divided by the elapsed time. And all that is happening in the y direction. So this first thing in parentheses is just our average acceleration in the x direction. And the second thing in parentheses is just our average acceleration in the y direction. So these are the definitions we're going to be working with going forward in today's lecture. And just like we did in last lecture, we're going to look at physically interesting situations, like situations where our object is moving at a constant velocity. And we're going to find out those equations. We're also going to look at the situation where our object is experiencing a constant average acceleration. And then we're going to see sort of what falls out of that. And you'll notice that the equations that we get from this procedure are going to look remarkably similar to the ones that we got in yesterday's lecture. Right. So now that we've gotten all those definitions out of the way, let's talk about motion in 2D with constant velocity. Let's look at situations where our object is moving with a constant velocity. So I've said this before, but since it's more relevant to our immediate discussion, I'll repeat it again. I said before that accelerations change velocities and velocities change positions. So if we're dealing with something that is experiencing a constant velocity, that means its velocity is not changing. But what does it mean for a vector quantity, like a velocity, to not change? Well, we know that velocity, being a vector, has both a magnitude and a direction. So what this means is it can't have its magnitude change. The magnitude of the velocity can't change. It can't be going faster and it can't be slowing down, because otherwise that would be changing and that would mean there was acceleration. And also its direction can't change. We can't move in another direction without acceleration being present. So the way that we represent that in mathematics is to say that the magnitude of our acceleration has to be 0. So the magnitude of our acceleration vector must be 0 with units of meters per second squared. But since our acceleration is a vector also, right, in 2 dimensions, it has an x component and has a y component. So for the magnitude to be 0, that means that both the x and y components of the acceleration must be 0. So the x component of our acceleration must be 0, and the y component of our acceleration must be 0. If either one of these wasn't the case, right, let's say that ax is some other number other than 0, then what would happen is our velocity, its x component, would change. So for motion in 2D with constant velocity, we need both components of our 2-dimensional acceleration vector to be 0, right? We need ax to be 0, and we need ay to be 0. So it turns out then when we're looking at the position of something that has a constant velocity, our position is given by r, right? Our 2D position vector is given by our initial position plus our velocity times time. But keep in mind that both r0, our initial position vector, and our velocity v are 2-dimensional vectors. So they have an x component and they have a y component. So we can actually break this down. So r0 is going to be some amount x0 in the x direction plus some amount y0 in the y direction. And then we're going to look at the second term here, so plus the velocity. So the velocity also has x and y components. We have an x component of our velocity in the x direction plus the y component of our velocity in the y direction. And all of that's multiplied by time. So I'm going to take this time and I'm going to multiply it through. I'm going to quickly rewrite this equation. So r0 stays the same. It's x0 in the x direction plus y0 in the y direction plus, and again, we're multiplying a vector v by a scalar t. And the way that we do that is we take our scalar and we just distribute it to each of the components of our vector. So this becomes vx times t in the x direction plus vy times time in the y direction. And last but not least, the way that we add these two vectors together is by adding their like components. So we take the x components of both vectors and add them together, and then we take the y components of both vectors and add them together. So overall, this becomes, if we group the x components, we have x naught plus the x component of our second term here, which is vx, the x component of our velocity, times time. Right, and all that is happening in the x direction, plus the y component stuff. So we have the y component of our initial position, which is y naught, plus the y component of our velocity times time. And this is all happening in the y direction. So you'll notice something here, that motion in 2 dimensions is just decomposed into two 1D motions. So this looks exactly like what we got from the last lecture. And this is the same thing, just now pointing in the y direction. And so that's kind of the trick to motion in 2 dimensions. You just break the problem down into two 1-dimensional problems, right? Usually one in the x direction and one in the y direction. And then you sort of solve them simultaneously. And we'll work through a couple problems to see what I mean about that. So don't worry, we will get to that. So here I've whipped up a problem of motion in 2D with constant velocity, just to help us get more acquainted with actually working with these kinds of equations. So the example says that a car is moving from the origin with a velocity of 10 meters per second at an angle of 30 degrees with respect to the positive x-axis. The problem wants us to find the x and y components of this velocity vector. And after 5 minutes of driving, it wants us to find the displacement in the x direction, the displacement in the y direction, and the total distance traveled. So let's write down what we know about this. We know that our velocity vector, v, has a magnitude of 10 meters per second. We know that the angle of this vector is at 30 degrees with respect to the positive x-axis. And I'll draw a picture to make this a little bit clearer. And the problem wants us to find vx, vy, the y components of this velocity vector, as well as how far we've gone in the x direction, the y direction, and the total distance traveled after 5 minutes of driving. So first, let's try tackling the parts A and B here. So what we're going to do, we're going to draw our coordinate system. Right, so this is our y direction, this is our x direction, like this, and we've got some velocity vector v, points like that. And so we know that the velocity vector has a magnitude of 10 meters per second. And the problem is asking us to find the x and y components of this velocity vector. So what we're going to do, we're going to make a right triangle by going to the point where the vector points, dropping it down. And so this part here that's going in the x direction, this is the x component of the vector. And similarly, this part here is the y component. That is how much it goes up in the y direction. But I can also just move it over here. The second bit of information that the problem tells us is that the angle between this velocity vector and the positive x-axis, right, this is the positive x-axis, and it says that the angle between these two things is 30 degrees. So this angle right here is 30 degrees. And we know how to find the x and y components of a vector given its magnitude as well as its angle with respect to the positive x-axis. So the x component of a vector is given by its magnitude v, times cosine of the angle between that vector and the positive x-axis. So in this case, the magnitude is 10 meters per second, can't leave off the units, times cosine of 30 degrees. Right, so cosine of 30 degrees, you can take that and plug it into a calculator. and it should give you something back like 0.866 or whatever. So multiplying both of this stuff together, this gives us an x component of about 8.7 meters per second, let's call it. Right? And we can do the same thing to figure out the y component of this velocity. So that's just equal to the magnitude of the velocity vector times sine of the angle between the velocity vector and the positive x-axis. Right, so this is the magnitude of the velocity vector, which is 10 meters per second, times sine of 30 degrees. And this gives us 5 meters per second. So we've already figured out part A and B of this problem. So that's not too bad. Now to figure out parts C, so first we need to convert 5 minutes of driving into seconds. So let's do that really quick. So 5 minutes of driving is how much time has elapsed. That's 5 minutes. But we know that there are 60 seconds in 1 minute. Do a little bit of quick unit conversion here. So the units of minutes up top get canceled by the units of minutes on the bottom. And then we're left with an answer in units of seconds, which is what we want. So we have 50 times 60, or 5 times 60, excuse me. This gives us a time of 300 seconds. Okay. So now we can begin to solve for our displacement in the x direction, the y direction, and the total distance traveled. So the way that we're going to solve for delta x and delta y is by using the definitions that we have just written down. So we said that in 2 dimensions, at constant velocity, our position vector, r, is equal to x naught plus vxt. This is in the x direction, plus y naught plus vyt in the y direction. And this is equal to our final position x in the x direction plus our final position y in the y direction. So why do I bring this up? Because our final position has to be equal to this first thing in parentheses, and our final position in the y direction is equal to this stuff in the second set of parentheses. So what we can do is say that x is equal to x naught plus vx times time. And we can also write that y is equal to y naught plus vy times time. So notice what happens if we subtract off our initial position x naught and y naught from both sides. So for this first equation, I'm going to subtract off x naught from both sides. Subtract it off. So then we're going to have x minus x naught is equal to vx times time. And if we do the same thing for the y position, right, we subtract off the initial position in the y direction from both sides, we get y minus y naught is equal to vyt. But notice that the things on the left-hand side of these equations are just our displacements in the x and y directions respectively. So for our first equation, the one with the x's, we have our displacement in the x direction is equal to the velocity in the x direction times time. And our displacement in the y direction is equal to the y component of our velocity times time. Right? And luckily, we just solved for both of these things. We know what Vx is, that's 8.7 meters per second. And we know what Vy is, 5 meters per second. And we've already solved for the time in units of seconds, so that's 300 seconds. So we can actually just plug stuff in. So the x component of our velocity is 8.7 meters per second times the time of 300 seconds. And in the y direction, we have the displacement in the y direction is equal to our velocity in the y direction, which is 5 meters per second, times the elapsed time of 300 seconds. So we get that our displacement in the x direction, right? If you were actually to punch in 8.7 times 300, our displacement in the x direction is equal to 2,610 meters, and our displacement in the y direction is equal to 1,500 meters, so 1,500 meters. And so this is the first part of part C. Right? So part C says, after 5 minutes of driving, what is the displacement in the x direction, the y direction? And then finally, let's figure out the total distance traveled. So the total distance traveled, in our case, is going to be the displacement, or the magnitude of the displacement for our, what is this, a car? Yeah, it's going to be the total displacement of our car. So if you remember our definition for the displacement in 2 dimensions, that's equal to our displacement in the x direction plus our displacement in the y direction, like that. And if we want to find the magnitude of a vector, such as the displacement, what we do is we take the square root of the x component of our vector squared. In this case, it's going to be our displacement in the x direction, plus our y component squared, which in this case is delta y squared. Right? And it looks like I'm going to have to write it down here. So we have that our displacement, or the total distance traveled by this car, is equal to the square root of delta x squared. We found that delta x was 2,610 meters squared, plus our y component squared, delta y. So that's 1,500 meters squared. And so the total distance traveled by this car over the course of 5 minutes is equal to 3,010 meters. So there we have it. So now that we've finished talking about constant velocity equations in 2 dimensions, let's move on to the next step, which is talking about things that have constant acceleration, but that are also potentially moving in 2 dimensions, so 2D motion. So to begin with, constant acceleration means that our acceleration vector, okay, is a constant. Whatever it is, it's not changing. So for this acceleration vector to be constant, that means that its components also have to be constant. So in component form, this means that the x component of our acceleration has to be constant, and our y component for our acceleration vector also has to be constant. Just like that. Then next up, our second constant acceleration equation in 2 dimensions is that our final velocity is equal to our initial velocity vector. I don't know why it keeps doing that. So our final velocity is equal to our initial velocity vector plus our acceleration times time. And again, you can break this up into component form. So this means that our final velocity in the x direction is equal to our initial velocity in the x direction, which I denote by v naught sub x, plus our acceleration in the x direction times time. And the y component of this is that our final velocity in the y direction is equal to our initial velocity in the y direction plus our acceleration in the y direction times time. So for a third equation, we have that our position is equal to our initial position plus our velocity times time plus 1/2 times our acceleration vector times time squared. And just like with the previous two equations, we can also break this one down into its x and y components. So all of this should look familiar. So we have our final position in the x direction is equal to our initial position in the x direction plus the x component of our velocity, our initial velocity, times time, plus 1/2 times our acceleration in the x direction, times time squared. And similarly for y. Except now we're using our initial position in the y direction, y naught, plus our initial velocity in the y direction, times time, plus 1/2 times our acceleration in the y direction, times time squared. Right? So all of these equations should sort of remind you of one-dimensional motion. And like I mentioned earlier, 2D motion is really just two 1D motion problems sort of put together. And it's not really any more difficult or complicated than that. So, and for our fourth and final constant acceleration equation, we have that, I'm just going to actually write this one down in component form. We have that our final velocity in the x direction squared minus our initial velocity in the x direction squared is equal to 2 times our acceleration in the x direction times the magnitude of the displacement in the x direction. So this is the x component version of this, and the y component version is the same thing, but now we're using y component stuff. So this is the initial velocity in the y direction squared. We have 2 times our acceleration in the y direction times the magnitude of our displacement in the y direction. So these 4 sets of equations, right, make up what we call the constant acceleration equations in 2 dimensions. So now I'd like to look at an example that sort of puts this stuff into practice. This example is a little bit longer. So in this example, we have a car starts traveling at a velocity of 10 meters per second at an angle of 30 degrees with respect to the positive x-axis. So this is sort of the same way that the previous example started, but now it has an acceleration of 5 meters per second squared, presumably also in the same direction as its velocity, so at 30 degrees with respect to the positive x-axis. So the question says, after 10 kilometers of driving in the same direction, it wants us to find the initial components of our velocity, the x and y components of our acceleration vector, the time it takes to actually drive that 10 kilometers, our final components for our velocity in the x and y direction after we've driven 10 kilometers. And it also wants us to find our displacement in the x and y directions after that amount of time. So to begin with, let's start by solving for a and b almost simultaneously. So for a, we can draw a coordinate system like this, right, where this is the x direction, vertical is the y direction, and we have this vector v, which points like this. And this initial vector v has a magnitude of 10 meters per second, and it's at an angle of 30 degrees with respect to the x-axis. So similarly, I'm going to redraw this. Our acceleration vector points in the same direction. So I'm going to draw the x and y axis here, and then we've got some acceleration vector, but the magnitude of this acceleration vector is 5 meters per second squared. Right, meters per second squared. And it's also presumably going the same direction, so it's also at 30 degrees. And so parts A and B are asking us to find the components of our initial velocity vector and for our acceleration vector. So let's do that. So if we drop a line down from where our vectors are pointing, we make a right triangle. I'm going to zoom in a little bit now. And so this part here is the x component for our initial velocity vector. This part here is the y component for our initial velocity vector. if we do the same thing with the acceleration, and this part here is the x component for acceleration, and this vertical component here is our y component for our acceleration vector. And so using the trigonometry that we know that the x component for our velocity vector, v naught x, is equal to the magnitude of our initial velocity vector times cosine of theta. All right, so that's going to be 10 meters per second times cosine of our angle, which is 30 degrees. Actually, move this over a little bit. Just like that. And so if you punch this into a calculator, you should get roughly 8.7 meters per second, because cosine of 30 degrees is 0.866. If you multiply that by 10, you get 8.66, which we're going to round up to 8.7. And so we can do something similar for the y component of our initial velocity vector, except now, instead of using cosine, we use sine of our angle theta. So it's our magnitude, which is 10 meters per second, times sine of 30 degrees. This is going to be 5 meters per second. So these two right here are the answers to part A. So one answer, that's the second part of part A. And we can do something similar to find the x and y components for our acceleration. So for acceleration, our x component is just equal to the magnitude of our vector times cosine of the angle theta with respect to the positive x-axis. So this is going to be 5 meters per second squared multiplied by cosine 30 degrees. So this is going to be equal to about 4.3 meters per second squared. Meters per second squared. And we could do something similar with the y component, right? It's our magnitude times sine of theta, which is equal to 5 meters per second squared, times sine of 30 degrees. Right? And this is going to be equal to 2.5 meters per second squared. Meters per second squared. And so that's part B of our problem. Right now we found the x and y components for both our initial velocity vector as well as our acceleration vector. So now let's look at part C. So to solve for part C, we're going to make use of the fact that our displacement is going to be 10 kilometers away from the origin at an angle of 30 degrees with respect to the positive x-axis. I'm going to draw another picture. We have our y-axis, our x-axis. And so this problem is saying that we have a vector, our displacement is 10 kilometers. So this is our final position R, has a magnitude of 10 kilometers. And this is at an angle of 30 degrees because we were driving, at an angle of 30 degrees. So we're going to solve this similar to how we solved these first two parts. So first I'm going to drop a line like this. So we have a right triangle. And then notice here that the x component of this displacement vector is going to be our delta x. And we could also solve for delta y. In fact, yeah, might as well, since that's also part E. So let's do that as well. Delta y. And I'm kind of skipping around a little bit. That's okay. So we know that this is, this position vector has a magnitude of 10 kilometers. And we know that this is 30 degrees. This angle here is 30 degrees. So we can do basically what we did for parts A and B to find part E of this problem. So we know that our delta x is going to be equal to the magnitude of our displacement vector or our position vector. So it's going to be 10 here. I say position, but this is also really just our displacement. I'm using them interchangeably here, which is kind of irresponsible on my part. So this is really our displacement after driving that 10 kilometers. So the x, so our displacement in the x direction, delta x, is going to be equal to the magnitude of our displacement vector, which is 10 kilometers, multiplied by cosine of 30 degrees. Right. So this is going to be equal to 8.7 kilometers roughly. And then we can do something similar with y to find our displacement in the y direction. That's equal to the magnitude of our displacement vector times sine of 30 degrees. And that's going to be equal to about 5 kilometers, which is all well and good. So I think at this point it would be fine to leave things in terms of kilometers, but we would like to use this information to help us solve for how long this drive took. Right, we're trying to find t. So we want to convert from kilometers into meters, because that's one of the units that we always want to be working in. So we know that 1 kilometer has 1,000 meters in it. So delta x is equal to 8.7 kilometers. And we know that there are 1,000 meters in 1 kilometer. Let me just move this over a little bit. Very good. And so kilometers cancel out. And then we're left with an answer of 8,700 meters. 8,700 meters. And so that's how far we've gone in the x direction since we started driving. And then for our displacement in the y direction, right, that's going to be 5 kilometers times our conversion factor, which is 1,000 meters per 1 kilometer. And so this becomes 5,000 meters, just like that. So this is actually part E. But we solve for it here because it's going to be useful. So now we can use this information to help us figure out how long this drive took. So if we start with the displacement in the y direction, for example, and I'm only choosing this because we kind of rounded to get delta x, but 5 times, where is it? 5 or 10 times sine of 30 degrees is exactly 5. So with this one, we didn't do any rounding. So we're going to get a more precise answer for our time if we use this one. So delta y, our displacement in the y direction, is equal to the y component of our initial velocity times time plus 1/2 times the y component of our acceleration times time squared. Right. And so we know the left-hand side is 5,000 meters. On the right-hand side, we have the y component of our initial velocity vector. Well, we solved for that in part A. That's 5 meters per second. So the right-hand side is 5 meters per second times t star, right? The amount of time it takes to actually drive that 10 kilometers, plus 1/2 times our acceleration in the y direction, which we can see right here is 2.5 meters per second squared. That's what we solved for earlier. That's 2.5 meters per second squared times t star squared. And so just like we did last lecture, we're going to solve this. So this is an example of a quadratic equation. So I'm going to move some things around. I'm going to subtract off 5,000 meters from both sides and sort of flip things left and right. And if you guys have any questions about this, please let me know. But to begin with, the left-hand side is we have 1/2 times 2.5. That's going to be 1.25. So we're going to have 1.25 meters per second squared times t star squared plus 5 times t star. So 5 meters per second times t star. And since I moved the 5,000 over, that's going to be minus 5,000 meters. And all that's equal to 0 meters. Right. So this is an example of a quadratic equation that we saw last lecture. And in order to solve it, we're going to need the quadratic formula, which says that well, t star is equal to minus b plus or minus the square root of b squared minus 4 times our value for a times our value for c, all divided by 2 times a. So in our case, a, our value for a, is 1.25. Our value for b is 5. And our value for c is minus 5,000, which is a little bigger than the other ones. Very good. So when we plug all this stuff into t star, or this quadratic formula, this will tell us what values of t satisfy this equation here. So we get that t star is equal to minus b, which is minus 5, plus or minus the square root of b squared. So b squared is 5 times 5, or 25, minus 4 times our value for a, which is 1.25, times our value for c, which is minus 5,000. There you go. So all of this is divided by 2 times our value for a. So 2 times 1.25 is 2.5, just like that. And so now we need to just simplify this a little bit. So we have t star is equal to minus 5 plus or minus. So the thing in the square root is equal to 25,000. 25. So all that is divided by 2.5. So we can simplify down again. So we have t star is equal to minus 5 plus or minus. So that all square rooted is about 158.2. All divided by 2.5. Plus or minus. There we go. So now we're dealing with the same situation that we experienced last time when we were solving the quadratic equation. So we have this choice of whether or not we're using the plus sign here or the minus sign here. Now, if we were to use the minus sign, we'd have minus 5 minus 158.2. So our time overall would be negative, which doesn't make any sense physically because we started our clocks from when the car started driving. And so we have to throw out that unphysical solution. So that means we have to use the plus sign here because otherwise we get negative time. It's not very physical. So t star, the time it takes to drive this 10 kilometers is equal to minus 5 plus 158.2, all divided by 2.5. And so this gives us a time, t star, of about 61.3 seconds. All right, so this person did 10 kilometers in about a minute, which seems kind of fast, but who might I judge? Okay, so that's part C. So now looking at this, we've solved part A, part B, part C, and oddly enough, part E. So now we're going to solve for part D. So we're going to find the final velocity in x and the final velocity in the y direction. More specifically, we're finding the components of the final velocity. So we know that our final, or the component of our final velocity vector in the x direction is equal to our x component for our initial velocity vector plus our acceleration in the x direction times time. And then we have something similar for the y stuff. It's like this. So we have the x component of our final velocity vector is equal to our initial velocity vector's x component, which it's been a while, so 8.7 roughly. It's about 8.7 meters per second. zoom in a little, plus our acceleration in the x direction, which is about 4.3 meters per second squared. Just like that. Times how long it takes us to drive that 10 kilometers, which we just found to be the 61.3 seconds. Right. And if you punch all this to a calculator, you get 272.3 roughly meters per second. And for our y component, for our final velocity, we have the initial y component for our velocity vector, which is 5 meters per second. 5 meters per second, plus our acceleration in the y direction, which is 2.5 meters per second squared. Multiplied by how long it takes us to drive that far, which is 61.3 seconds. And this is equal to 158.3 seconds. Or excuse me, 158.3 meters per second. So this guy is going pretty fast. And so that's the whole problem. So it's at this point that we reach the first major milestone of a Physics 1 course, and that is projectile motion. Everything that we did in the previous couple lectures leading up to this point were really in preparation for this moment. So projectile motion is a two-dimensional motion where the only acceleration acting on an object is the acceleration due to gravity. So in essence, it's actually kind of a free fall problem. And so what this means is that our acceleration vector, right, because we're working in two dimensions, our acceleration vector has 0 meters per second in the x direction. That is, there's no acceleration in the x direction. But in the y direction, we have minus 9.8 meters per second squared acting on our object in the y direction. So an example of projectile motion would be like, well, I don't know. So we draw a little two-dimensional coordinate system here. Right, this is more of a sketch, really. So we have our x-axis, we have our y-axis on the vertical axis, and then let me see if I can't switch over to something else here. Go dotted lines. And so our object starts from the origin, and it gets shot out of a cannon or thrown or kicked. However it gets launched, it doesn't really matter. But then, it gets launched, and then, it's got a trajectory that kind of looks like that in general. And so at each point, the velocity of this object is perpendicular to its trajectory. So this here is V0, right? And at every single point, might actually just switch up the colors so it's a little bit easier to see. So at every single point of this trajectory, its velocity is going to be perpendicular. Not perpendicular, it's going to be tangent to the trajectory here. Right, so at this point, the velocity looks like this. This is v at a later time. And then towards the end, its velocity is still going to be tangential to its trajectory. So it's going to look something kind of like this. Right. And so the things that we need from projectile motion, the things that we need to do the problem with, are we need to know the height at which our object is launched. In this little diagram that I have here, this object is presumably launched from ground level height, because we typically say that the ground is at y is equal to 0, unless otherwise stated. So we need to know the initial height of the object. And more importantly, we need to know the initial velocity of the object. And with these two pieces of information, coupled with the fact that we know the acceleration is only acting in the y direction and is pointing downwards, we can use this to figure out the trajectory of our projectile. And so I think when we see a few problems working with this stuff, you guys will get familiar with it. And again, if you have any questions at any point in time, please just ask about it, okay? So now I'm gonna write down the equations for projectile motion. So the x components, that is the equations that we're gonna be looking at in the x direction, are threefold, right? So the first important bit of information about our x component stuff is that there's no acceleration in the x direction. So what does this mean? This means that our object, for as long as it's in the air for, will be traveling forwards in the x direction at a constant velocity. And that's going to be equal to the x component of our initial velocity vector, right? Because if there's no acceleration in the x direction, then that means it can't be going faster or slower in that direction. So when we're considering these projectile motion problems, we're going to be simplifying things a bit. We're going to pretend like there isn't air resistance acting on our object, right? If there was air resistance acting on our object, you know, as it flew, the air would be pushing back on it and it would slow it down. If you've ever been riding in a car with the window down and you've stuck your hand out, right, you can see that the air pushes back on your hand and it's slowing down your hand from going forward. And so we're going to pretend like that sort of doesn't happen. We're pretending like Earth doesn't have an air atmosphere. So that's not really physical. In more complicated treatments of projectile motion, you can add that back in. And so this, you know, our x component of our acceleration wouldn't be zero, but in this course, we're not going to see that. So whenever we're dealing with a projectile motion problem, you can safely assume that the x component of our acceleration is going to be zero. So that's one of the first things we need to know. Second up in the x direction, we see that our final position in the x direction is equal to our initial position, x naught, plus the x component of our initial velocity vector times time. Right, this is the x component from those constant velocity equations that we saw earlier. And last but not least, for the x component stuff, we have that our final velocity in the x direction is equal to our initial velocity's x component. So this is going to be a constant, right, for the reasons that I mentioned earlier. So if we're saying that there's no component of the acceleration in the x direction, then our x component for our velocity can't change. So for all intents and purposes, our final velocity x component, that is like the x component of this velocity when it hits the ground or whatever, is going to be the same as when it started. So we're just going to consider that a constant. So that's pretty much it for the x component stuff. Now let's look at the y component stuff. All right, we got the y component stuff. So the first thing we need to know about the y component stuff is that our acceleration in the y direction is going to be equal to g, which is going to be minus 9.8 meters per second squared. So the second thing we need to know about projectile motion for stuff in the y direction is that the height of our object is equal to the initial height of our object plus the y component for our initial velocity vector times time plus 1/2 times the acceleration due to gravity times time squared. For our third equation in the y direction, we have that our final velocity in the y direction at any given point in time is equal to our initial velocity in the y direction plus g times t, right? Our acceleration in the y direction times time. And last but not least, fourth relevant equation for our y component stuff when talking about projectile motion is that our final velocity squared in the y direction minus our initial velocity in the y direction squared, that's going to be equal to 2 times our acceleration in the y direction, which is just g, times our displacement in the y direction. Right. So these 3 equations for our x components and these 4 equations for our y components make up everything we need to know about projectile motion. So let's look at a problem to sort of help us understand these equations and how to use them going forward. All right, so here's an example to sort of help us get used to projectile motion. So in this example, it says that a ball is thrown at an angle of 60 degrees with an initial velocity of 100 meters per second. So the problem wants us to find the time it takes to reach the maximum height, as well as the range. So how far this ball is actually thrown. So just want to point out that, let's switch over here, that the max height is the height here. Let's call this max height h. This is going to be the max height. And like the name implies, it is the maximum height that this object reaches. And furthermore, the range is how far the object goes. So the object starts at the origin. It goes approximately over here. So the range here is r, and that's just how far the ball actually goes. You can also think of this, instead of r, think of this as x, or even better, as the displacement in the x direction. So let's write down a little bit what we know about this problem. So I'm just going to zoom out a little bit. There we go. Okay, so to begin with, the problem doesn't say otherwise. So we can assume that the ball is starting at a position of 0, 0, right? It's being thrown from this origin. So its initial position, x naught, right? Its initial position in the x direction, we can assume that to be 0 meters. And we can assume that it's also being thrown from a height of 0. So its initial height above the ground, we'll say, is 0. Right? And next up, it says that the ball is thrown at an angle of 60 degrees. So here theta is going to be 60 degrees. And it's thrown with a velocity of 100 meters per second at this angle of 60 degrees. So it has an initial velocity, magnitude. So this is just the magnitude of our initial velocity vector. Right? Of 100 meters per second. And so it's asking the time it takes to reach the max height. So we're trying to find t, the max height, or h, as well as the range. So let's start. So anytime that you're trying to solve a projectile motion problem, the first thing that you want to usually do is draw a picture, because that just helps you get your bearings. But since I've already drawn a picture here, the next step is to take our initial velocity vector and break it up into its x and y components. So I'm going to zoom in a bit because it's getting hard for me to write. So I'm just going to make a quick little diagram of our initial velocity vector. Right, that's the x-axis, this vertical axis is the y-axis, and our vector looks, I don't know, something like that. Now, it's more 45 degrees, but this is not drawn to scale. So this angle here is 60 degrees. And we're going to make a triangle, right triangle, just like we've done before. Right, so this is our initial velocity vector. And it has a magnitude of 100 meters per second. Right. So we want to find its x component. So this is the initial velocity in the x direction. And we also want to find its y component, the initial velocity in the y direction. So we're trying to find these two things. And we can do that because we know that the initial velocity in the x direction right? When we break down a vector in the x direction, that's equal to its magnitude times cosine of the angle between the vector and the positive x-axis. So in this case, the magnitude is going to be 100 meters per second. And it's going to be multiplied by cosine of 60 degrees. So this is going to be equal to 50 meters per second. 50 meters per second. And the y component for our initial velocity vector is the magnitude of the initial velocity vector times sine of 60 degrees, or sine of theta. So it's going to be 100 meters per second times sine of 60 degrees. And that's going to be equal to roughly 87 meters per second. Very good. Okay, so now that we've broken up our initial velocity vector into its x and y components, let's start by solving for part A. So we want to figure out how long it takes to reach the maximum height. Well, that's not too bad. So something that helps us figure out the maximum height in this case is the equation that our velocity in the y direction is equal to our velocity in our initial velocity in the y direction plus our acceleration times time, right? But then I want you guys to note that at maximum height, our final velocity in the y direction is going to be 0. All right, so the left-hand side of this is going to be 0 meters per second. I'll explain a little bit more about that. And on the right-hand side, we have our initial velocity in the y direction. So it's about 87 meters per second. We have plus the acceleration in the y direction, which is just g. So it's going to be minus 9.8 meters per second squared times time. And then if I subtract off, or in fact, if I add this term to both sides, then we get on one side positive 9.8 meters per second squared times time is equal to 87 meters per second. And so note that this time that we're solving for is the time it takes to reach maximum height. So now if I divide both sides by 9.8, we get that the time it takes to reach the maximum height is equal to about 8.88 seconds. But let's call it 8.9 seconds. Why not? All right, so let's take a step back. Why is the y component of our velocity vector 0 at maximum height? So we go back up to our picture. So if you guys remember, I said that at every point along this projectile's path, the velocity vector is tangential to the path itself. So the reason why this is important is because the way that we define the max height is the point where the velocity of our object in the y direction is 0. And you can kind of think of it as, when you first, shoot the object up or throw the object up, whatever, it goes up and up and up, and it slows down and it slows down and it slows down until it reaches its max height, at which point it stops moving in the y direction, right? It can still be traveling forward in the x direction, but in the y direction, it has to come to a brief stop before then turning around and then falling back down again. And so at that point where the y component of our velocity is 0, that's when we say that that is the max height. It is at that point in time we say the object has reached its max height, or when it slows down and down and down until it reaches its maximum height, and then the y component is 0, and then the y direction turns around, and now it starts falling back down towards the earth. So that's why we say that the y component of the velocity at max height is 0. Right? And so apparently the time it takes for this ball to reach its maximum height is about 8.9 seconds. I would also like to point out that this person has an absolute cannon for an arm. because 100 meters per second is really, really fast. The fact that it reaches its max height after almost 9 seconds of airtime is actually pretty impressive. All right, so that's it for the time. And then part B is asking, well, what is the actual maximum height of this object? So we can figure that out in 2 ways, right? If we go back to our y component equations, we know that we can find the maximum height by plugging in the time it takes to reach maximum height, as well as the initial velocities, y component, and the acceleration. All right, we could do that. Or we could use this equation down here, because this displacement in the y direction on the right-hand side, right? We can solve that for the maximum height of this ball. Because we know that, at max height, its velocity in the y direction is 0. And so we can solve this to find delta y. For this particular instance, I'm actually going to use equation 4, and we're going to work through it that way. All right, so now working on to part B, we have to find the max height. I'm just going to recopy the equation here. So the y component of our velocity squared minus the y component of our initial velocity squared is equal to 2 times our acceleration in the y direction times our displacement in the y direction delta y. So at max height, our final velocity's y component is 0. Right, so this is 0 meters per second. All that is squared. We have minus the y component for our initial velocity vector, which we found to be about 87 meters per second. So this is 87 meters per second. We're going to square that. Then on the right-hand side, we have 2 times our acceleration in the y direction, which is minus 9.8 meters per second squared, times our displacement in the y direction, delta y. So now 0 squared is going to be 0. So we have 0 minus 87 squared. So 87 squared. The left-hand side becomes minus 7,569. Right, and it's going to have units of meters squared per second squared, right, because we squared it. So on the right-hand side, we have 2 times negative 9.8 meters per second squared. That's going to be minus 19.6 meters per second squared times our displacement delta y. But if you remember, our displacement in the y direction is just our final position minus our initial position. And we said earlier that our initial position for this case, right, is going to be 0, because the problem didn't say that we're starting at an initial height of whatever. If it had, we wouldn't have been able to do this, but we can just assume that our object is being thrown from a height of 0. Right? Because of that, this is going to be 0. And now if we divide both sides by minus 19.6, we get that the height, our max height in this case, is going to be equal to 7,569 meters squared per second squared divided by 19.6 meters per second squared, meters squared per second squared. Right, where I've canceled out the minus signs. So this is going to be equal to, a height of about 386 meters. 386 meters. So we've said that our max height we're going to denote as h. So it's going to be 386 meters. Okay. So that's part B of this problem. So we're already 2/3 of the way through. It's pretty good. So the last thing that this problem is asking us to find is the range of the ball thrown. So in order to find the total distance that the ball was thrown, we're going to make use of this equation from our x component equations that says that our final position in the x direction is equal to our initial position in the x direction plus the initial velocity in the x direction times time. So the good news is, since the ball was thrown from x naught is equal to 0, that means that this term is gone. That's 0. And so the final position of our ball is given by the x component of our initial velocity vector, which we know, times how long the ball was in flight for. T. So the problem is, we know what the initial velocity in the x direction is, but we don't know how long the ball was in flight for. We know how long it took for the ball to reach its maximum height, but that's not how long it took the ball to be thrown and then eventually hit the ground again. So we need to figure that out. But luckily, in this case, we can use a little bit of a trick. So I want you guys to notice that if our projectile, whatever it is, if it starts and lands at the same height, in this case, y is equal to 0, in this case, right? If it starts and lands at the same height, then I want you guys to notice it takes just as much time for the object to go up as it does to come back down again. That is the amount of time it took to reach its maximum height, call that T max or T height. So T max height. And you don't have to write this, I'm just writing it down. So the amount of time it takes to reach max height is the same amount of time it takes for it to fall back down again. And again, you don't have to write this, it's just something that I like to point out. So again, this only works if the object starts and lands at the same height. For example, if we had launched this ball from a box that started up here, and we try to figure out how long it took until it hit the ground, we wouldn't be able to use this trick. But because it's starting and landing at the same height, we can. So because of this, this says that the total amount of time it takes for this ball to hit the ground is max height time plus max height time, or 2 times the amount of time it took this ball to reach the max height. So call this T final, maybe, right, for when this ball hits the ground. This is going to be equal to 2 times T max height. Or you can call it, T max or whatever you want to call it. So in this case, we know that the time it took to reach the maximum height was what, 8.9 seconds, right? That was part A. So this is going to be 8.9 seconds. And so the total amount of time it took for this ball to be thrown and then eventually hit the ground is equal to 17.8 seconds. So now that we know how long it took this ball to be launched and then eventually hit the ground again, we can plug that in here to find out how far the ball went. So how far the ball went is equal to its initial velocity in the x direction, which off the top of my head, I've forgotten. All right, 50 meters per second. So 50 meters per second in the x direction times how long the ball was in flight for, or 17.8 seconds. Right. And this gives us a total distance of 890 meters. Right. So our ball, after being thrown by someone with an inhuman amount of strength, traveled 890 meters in the x direction. Right? And reached a max height of 386 meters. Which again is just, this is absolutely an insane distance. But that's the problem. And so most projectile motion problems are like this. Some might be a little bit harder, some might be a little bit simpler, but this is pretty much as hard as it's going to be. So if you guys are very comfortable with everything that we did here, with only minor tweaks, you're going to be very comfortable with other projectile motion problems, as we'll see. So now that we've done one projectile motion problem, I wanted to pull up this projectile motion simulator brought to you by physicsclassroom.com because I think it kind of helps get a little bit more physical intuition of what's going on with projectile motion problems. So I have it set to show the path of the projectile. And down here, we have some options that we can change. So here, the speed is the magnitude of our initial velocity. So it goes either from 0, in which case you're not really firing this thing at all, up to a max of 60 meters per second. We can also change the angle with which this thing is fired at. I'm going to set it to 45 for now. Actually, I'll just set it to 30, doesn't really matter. And last but not least, we can also change the height. There we go. We can also change the height of our initial projectile, right? And so I've set it to 40 meters per second at an angle of 30 degrees above the x-axis. And so let's just see what this looks like. All right, so the total distance traveled in the x direction is, about 140 meters. And let's see what happens if we do the same thing now. And reset, but we increase the speed. We increase the magnitude of the velocity with which this thing is fired. So I've increased it from 40 to 60. And now let's see what happens. All right, so that went a lot farther. So the first time, it only went to 140 meters roughly, but now it went to 318. So if you increase the speed while keeping the angle the same, you can in general expect that the projectile will go farther. Let's reset this. And so I'm going to bring the speed back to 40. And now I'm going to change the angle. So the angle is going to go from 30 to, let's say, 45 degrees. Let's start that one. All right, so it went a little bit farther than it did the first time, right? So the first time it was at 40 meters per second at an angle of 30 degrees, and it made a total distance of 140 meters. But when we bumped the angle up to 45 degrees, it made it to 163.27 meters, whatever. So last but not least, we can also change the height. So I'll just set it to max height, whatever. I'm going to set the angle back to 30 degrees. 30 degrees, there we go. Sorry, it's a little difficult. There we go. All right, so now we have basically the same initial conditions that we had when I launched this the first time, right? The magnitude of the initial velocity was 40 meters per second. We shot it at an angle of 30 degrees, but now I've raised it to a height of 120 meters. So now let's fire it and see how far it goes. Remember, the first time it only made it about 140 meters. Well, to no one's surprise, it made it a little bit farther, right? So it made it 256 meters instead of 140. And the reason for that's pretty simple. It's because the ball spent longer in the air before hitting the ground. So the longer the ball is in the air for, the further it can go, which kind of makes sense. So hopefully this little simulation has given you a little bit more physical intuition of what goes on to a projectile motion problem. If you guys want, you can play around with it yourselves, right? It's the physicsclassroom.com. It's got a lot of really good stuff. I just searched up projectile simulator or projectile motion simulator, and this was like one of the first things that popped up, so it's not too bad to find. All right, now for our last example of the day, we have that a ball is kicked from the top of a 20-meter building at an angle of 45 degrees with an initial speed of 50 meters per second. So the problem wants us to find the max height above the ground that the ball reaches, the time it takes for the ball to hit the ground, the range of the ball, so how far the ball goes in the x direction, and the speed at which it hits the ground. So we want to find the magnitude of the velocity of the ball just the instant before it hits the ground. So to begin with, let me draw a picture of the situation that we're dealing here. It's going to be similar to the final example I showed you guys with the projectile motion simulator. So we're going to have our x and y coordinates right So this is going to be the y direction. This is going to be the x direction. Like that. The vertical axis is the y direction. And the main difference between this problem and the last problem is that our ball is being kicked from a height of 20 meters. Sorry, this is a building. Our ball is being launched from this point. This is at a height of 20 meters. We're going to say that 0 meters is the ground down there, right? So this ball is launched, is kicked, goes up and then down. It's like that. Right, and the problem wants us to find a couple things about this. So to start with, ball is kicked at some initial velocity v naught. So let me just switch colors here. So the magnitude of our initial velocity vector, the problem tells us, is 50 meters per second. Meters per second. And the problem tells us that this ball is kicked at an angle of 45 degrees. So theta that we're going to be using is 45 degrees. What else does it say? The ball is kicked from the top of a 20-meter building. So the initial height of our ball, why not, is 20 meters above the ground. But notice that in the x direction, we're still starting at x is equal to 0. X is equal to 0. So just like that, 0 meters. And this is still a projectile motion problem. So in the x direction, our acceleration is going to be 0 meters per second squared. And in the y direction, our acceleration is going to be g, which is minus 9.8 meters per second squared. Okay, so part A is asking us to find the max height above the ground that the ball reaches. So if I draw a line like this, right, I want you guys to notice that the max height that this ball reaches above the ground is when it reaches right here. And notice that this distance between its max height above the ground and the distance or the height above which the ball started, so like this distance right here, this is going to be our max displacement in the y direction. Now, this is going to be the displacement of our ball when it's at max height. But then there's still this additional height of the building here, which we have to consider. Right, so this is 20 meters. So the total height of our building, which I'm going to call h, is going to be equal to our displacement at max height above where we started. Right, because if you remember, that delta y is just our final position in the y direction minus our initial position. So it's this little bit here. So our total height above the ground at max height is going to be our displacement in the y direction at max height plus the height of the building. Right. So part A is really asking us to find delta y. So let's do that. So to begin with, like we do with any projectile motion problem, we draw a picture, which we've done. And then part 2, which is almost equally as important, is we need to break our initial velocity into its x and y components. So let's do that. So I'm going to scroll down a little bit. So the x component of our initial velocity vector, v naught x, is equal to the magnitude of the velocity, magnitude of v naught, times cosine of the angle between our x-axis and our vector. So this is going to be, what, 50 meters per second times cosine of 45 degrees. Let me just move this over. So this is going to be equal to 35.4 meters per second. Right, so that's our x component and our y component, v naught y, for our initial velocity vector. It's going to be the magnitude of our initial velocity vector times sine instead. So that's going to be 50 meters per second times sine 45 degrees. Now, fun fact about sine and cosine: at 45 degrees, sine of 45 degrees is equal to cosine of 45 degrees. And so because of that, both the x and y components for the initial velocity vector are going to be the same. Right? If you punch these into a calculator, you'll find that they're exactly the same. Okay, well, now that we've found our components for our initial velocity vector, the next thing we need to do is decide how we're going to go about finding this displacement in the y direction at max height. So I'm going to use our fourth equation, right? The one that says that the final velocity in the y direction squared minus the initial velocity in the y direction squared is equal to 2 times the acceleration in the y direction times delta y. Right? And if you guys remember, at max height, the velocity in the y direction is 0. So because of that, on the left-hand side, we have 0 meters per second squared, 0 meters per second all squared, minus the y component for our initial velocity, which is 35.4 meters per second. We're going to square all that. And on the right-hand side, we have 2 times the acceleration in the y direction, which is minus 9.8 meters per second squared, times delta y. Very good. So on the left-hand side, we have 0 squared minus 35.4 squared. So the left-hand side is going to be minus, what is it, 1,250, roughly. It's a very close approximation. And it's going to be units of meters squared per second squared, just like that. And on the right-hand side, we have 2 times negative 9.8. So this is going to be minus, what is it, 19.6 meters per second squared times delta y. And then if we divide both sides by this minus 19.6 meters per second squared, we get that our displacement in the y direction at max height is going to be equal to 1,250 divided by 19.6. And it's going to be units of meters. This is going to be equal to about 63.8 meters. 63.8 meters. And so our final height now is this displacement in the y direction at max height, which is 63.8, plus 20 meters. So our max height above the ground is 63.8 meters, plus the initial height of the building, which is 20 meters. So this gives us a max height above the ground for the trajectory of this ball of 83.8 meters. Very good. All right, so that's part A. Now let's go back up and look at part B. So part B is asking for the time it takes for this thing to hit the ground. So in order to do this, we're going to need to make use of the quadratic formula again. So we're going to be using y, our height in the y direction, is equal to our initial height plus the initial y component of our velocity vector times time plus 1/2 acceleration of the y direction times time squared. So at some amount of time, right, t star, our ball will have finally hit the ground. And so when the ball finally hits the ground, we've said that's at a height of y is equal to 0. So on the left-hand side of this equation, we'll have 0 at a height of 0. And on the right-hand side, we have our initial height, just 20 meters, right? The top of that 20-meter building, plus the y component for our initial velocity vector. which was, I think, 35.4. Yeah, 35.4 meters per second. 5.4 meters per second times t star, right? The time it takes for this thing to hit the ground, plus 1/2 times negative 9.8 meters per second squared times t star squared. So we're going to need to use the quadratic formula to solve this, which is in a quadratic equation. So I'm going to rewrite this a little bit and move some things around. And if you guys have any questions about how I did this, please feel free to stop me and I will show you guys how I did this step by step. So I'm going to gloss over a little bit here. So we're going to have 4.9 meters per second squared times t star squared, right? So I just did 1/2 times negative 9.8 times t star squared. And I just, moved that over to the other side. And we're going to have plus negative 35.4 meters per second times t star. All right, I essentially just subtracted this term off from both sides. And then we have minus 20 meters. It's equal to 0 meters. All right, so I just moved some things around. And so using the quadratic formula, which says that t star, the time it takes for the ball to actually hit the ground, is going to be equal to minus b. So rewrite it here, plus or minus square root of b squared minus 4 times the value of a times the value of c, all divided by 2 times our value of a. So in this case, a is 4.9, b is minus 35.4. And then c is minus 20. Very good. So let's plug this stuff in. So we have t star is equal to minus b, so minus negative 35.4 or positive 35.4 plus or minus the square root of b squared, so minus 35.4. We're going to square that, minus 4 times a times c. That's all divided by 2 times a. So 2 times a is going to be 9.8. And so if you punch all this stuff in, you're going to want to make sure, again, to use the plus sign here, because the negative sign will give you a negative time, which we don't want. So if you use the plus sign, and you punch all this in, you get a time of flight. This is how long it takes for this thing to hit the ground, of about 7.6 seconds. Right? I'd also like to point out that we won't always be using this plus sign in this quadratic formula equation. Sometimes the correct answer is by using the minus sign, and we're going to have to treat this on a case-by-case basis. It just so happens that all the cases that I've shown you guys have required us to use the plus sign, but we very well might encounter things that require us to use the minus sign in the future. And when we do, I'll make sure to point it out to you guys, so don't worry about that. So for part B, the amount of time it takes for this thing to hit the ground is about 7.6 seconds. So now let's go back up, see what part C is all about. Right, it wants us to find the range. Okay, well, the range is not too bad, because we know that our position in the x direction is equal to our initial position in the x direction plus the x component for our initial velocity times time, just like that. And we just found out how long this thing was in flight for, 7.6 seconds. We know that x naught is equal to 0 because we're starting from 0. If I go back up to the picture, right, we're kicking this ball from a height of 20 meters, but we're still kicking it from an x of 0 meters, if that makes any sense, right? So the distance that our ball goes is given by x. And since x naught is 0, this is just equal to the x component for our initial velocity vector times the time of flight. So we have our final position is equal to the x component for our initial velocity, which we found to be 35.4 meters per second, times how long the ball was in flight for, which is 7.6 seconds. Right. And so solving for this gives us 269 meters for our range. So the total distance traveled in this case is 269 meters. So that wasn't too bad. Usually the hardest part about projectile motion problems are figuring out the time of flight, because you have to do the quadratic formula. But otherwise, it's really not too bad. Like once you get past that part, all the hard work is done. All right, so that's part C. Now part D says it wants us to figure out the speed at which it hits the ground. Okay, so the speed at which with which the ball hits the ground is given by the magnitude of the velocity vector just before this thing hits the ground. So if you remember, that's going to be equal to the x component of our final velocity squared plus the y component for our final velocity squared. And all of this is going to be under the square root. It's kind of an ugly square root sign, I apologize. I'm not very good at drawing them. So we need to figure out what the final velocity in the x direction is, and we also need to figure out what the final velocity in the y direction is. So let's begin by solving for that. So in the x case, we have that the final velocity in the x direction is equal to the initial velocity in the x direction plus our acceleration in the x direction times time. But for those of you who remember, we don't have an acceleration in the x direction for these projectile motion problems, right? Ax is equal to 0. The x component for our acceleration vector is going to be 0. And because of that, this whole second term is 0. So this ends up saying that our final velocity's x component is simply equal to our initial velocity's x component. Right? How fast the ball is traveling in the x direction does not change. And I believe this was equal to 35.4 meters per second. Right. Good. So that's this component here. But now we need to figure out how fast the ball was going in the y direction just before it hit the ground. So we can do that too. So the final velocity's y component is equal to the initial velocity's y component plus the acceleration in the y direction times time, or 35.4 meters per second plus minus 9.8 meters per second squared. Right, that's our acceleration in the y direction times the time it takes for this ball to hit the ground, which is 7.6 seconds. So punching all this in for the y component tells us that the y component for our final velocity vector, right before it hits the ground, is going to be minus 39.1 meters per second, right? Where this minus sign just indicates that the ball is traveling downwards, right? Which makes sense, it's falling. So now that we have the x and y components for our final velocity vector, we can plug them in here to figure out the magnitude or the speed with which the ball hits the ground. So the speed with which our ball hits the ground is going to be the x component of its final velocity, which is 35.4 meters per second. I'm going to square all that, plus the y component for our final velocity vector, which is minus 39.1 meters per second. We're going to square all that. Then we just take the square root of that. And this tells us that the ball hits the ground with a velocity of 52.7 meters per second. Right. And that's the last part of the problem. So with that, we've completed our lecture, and I'll see you guys tomorrow.